Okay, thank you. Um, so I'll be talking about this topic of quantum steering. And for those of you who are not familiar with the subject, this quantum steering is a type of non-local correlations in quantum mechanics, right? So what do I mean by that? Uh, to begin with, the idea of non-local correlation, when I say that this is a non-local correlation, I mean that the type of correlations that I will be dealing with are not compatible with a certain model or a certain classical notion of how the variables would be correlated. So here, for instance, I present two variables, A and B, and I say that they are correlated, but here in this case, I have this sort of a common cause that connects both of them, and the correlation appears because I don't know if this common cause, the actual value of this common cause, right? So here, in this sense, I give you a model of correlation, and I see that it is, in this case, non-local if my probabilities are incompatible with this notion. And we know already some types of correlations that are like this. So in quantum mechanics, for instance, we have this notion of separability and entanglement, which can be modeled in this way as well. But in the sense that we say that a quantum state is correlated, but in a classical sense, if we have this model with a classical common cause correlating them both. So I say that the state is entangled if it's not compatible with this type of model. And also in we can say the same thing about classical variables. If we have if we have this model where some variables can have some control parameters, but are correlated with a common cause that we don't know. So we say that a distribution, a probability distribution is local if it has this model, if corresponds to this model, and if not, we say that it presents some Bell non-locality. This way here, I am putting some, I'm making it more clear the causal relationship between the variables involved in this situation here. But it's more common to treat this as as a similar case to the case of entanglement. But assuming that we don't know which measurements or which quantum states are present here, so we usually deal with it in this sort of the black box type of modeling here. So this is the most common way to represent this, and then I'll be talking in this talk here along this way. So for quantum steering, we have the situation where we have the quantum state correlated to a measurement that is made on the other side. So here I show you the type of most commonly known as the EPR paradox presented by Aston, Podolsky, and Rosen, where we have the quantum state correlated to measurements. In this case, we know them, the position and momentum. But in the general case, I will not be concerned with the actual measurement that's been done here in the side, but only with the notion that my quantum state is being, in a sense, prepared at a distance by measurements that are done on the other side, and I don't actually specify them. So this was formalized by, this is the model formalized by Wiseman, Jones, and Doherty, and they have introduced this local classical model, which corresponds to the local hidden states model for this type of system, for this type of correlation. And if my system is not corresponding to this decomposition here, I say that I have quantum steering. So in this sense, the quantum steering is the no-local correlation, which is between a generic measurement and a quantum state on the other side. Or if I prefer the notion of a black box being on one side, or if the party doesn't have don't have access to the inner mechanisms of the device, I say that it is like a correlation between a quantum state and the untrusted measurements that are being performed on one side. So it's kind of, from this diagram, it's somewhat clear that it's a kind of an intermediate scenario between the entanglement and Bell non-locality. So in this case, to describe my system, I have this list of subnormalized states, which encompasses the information on both sides. So I have the quantum system on one side. If I just multiply the probabilities that is associated to the untrusted measurement size, and to the state which is associated with the other, and I have complete information in these subnormalized states, in these states which are less than one trace, because if I take the trace out, I recover the probability which is associated to the black box, and if I normalize the state, I recover the quantum state which is on the other side. So I want to see if this in this list here, if in this list here I have the type of decomposition where in terms of classical correlations. So we know also that quantum steering is a resource for certain types of quantum information processing tasks, such as the subchannel discrimination or one-side device-independent quantum key distribution, right? And in a sense, if I consider that steering is useful for these tasks, and I have stronger, in a certain sense, steering, I have better performance on these tasks, I have the notion that steering is a resource for this, right? And in this case, I can characterize these systems, these so-called assemblages, which has the classical model, the local hidden states model, as the resourceless systems for this case. So systems that doesn't respond well to the task at hand. And in this situation, I can formulate a resource theory for quantum steering by providing also the free operations, which are these operations that preserve my unsteerable system. So operations, type of mappings of quantum assemblages onto other quantum assemblages, which do not create steering out of resourceless systems. This was done by Leandro Olita and Rodrigo Gallego in 2014, where they developed this framework of local operations and one-way classical communications, which entails a class of of free operations, where then you have the possibility to on the quantum side of the system, to perform any type of map, any type of completely positive trace preserving map. On the other side, you can deal classically. You can perform any type of classical computation with the variables that the black box side may have. And also, we allow this one-way classical communication. So it's some sort of an in-between between the classical framework of the traditional framework of local operations and classical communications for entanglement, and the classical these operations named wirings for Bell non-locality type of scenario. So these fully device-independent scenarios. So combining these two things, these free operations and the resourceless states, we have the resource theory for steering. So here, the notion is we have a resource theory. This allows us to do certain types of manipulations on the system and to analyze the systems in a certain way. And this has provides us with some other tools to analyze the non-locality. In this, one particular tool is the quantifier for the resource, which we can define as functions that do not increase when we perform free operations, and that are null for resourceless states. And also we can compare the different types of non-locality, and one of the some results that were presented also in that work from Olit and Gallego was the notion that a singlet assemblage is not well defined for quantum steering, so we don't have the same type of notion that you have a maximally entangled quantum state, and then you can, by performing the free operations, reach any other quantum state. Here you have this is non-existent. This is not non-existent. We have infinite classes of quantum of assemblages, and this also opens up the door to explore more complex scenarios with quantum steering. So it's usually we deal with two parties, one party device independent, the other device dependent, and or certain simple tasks with a multipartite scenario. So here we can ask some interesting questions, such as can I distill quantum steering using this one-way LOCC framework, or considering more parties, can I say that a quantum steering, or better, how can I define that a system is actually unsteerable or not, has or doesn't the resource? So here for my first work that I'm going to present, I have shown the notion of distillation. So it was work done in collaboration with Márcio Tadei, Paulo Sayum in the experimental part, Rodrigo Gallego, and Leandro Olita. So here we showed that that the quantum steering is actually distillable. So we can concentrate steering from, if I get multiple copies of weakly related systems, I can concentrate these correlations onto fewer systems. So I can, in a sense, revert degradation of the correlation by consuming some of the copies of the system. And to do that, we have we have adapted two protocols to the steering case. In the case, we have adapted the local filtering known from entanglement by Bennett, Bessard, and some others. And in other protocol we have dealt with also was based on a coherence distillation protocol, but I will not talk about this topic here. I will concentrate on this local filtering protocol, but since we have also done an experiment in it. And the essential idea is that we consider states that, here is not normalized, but states that differ from the maximal correlation by just a difference in the population between the levels. So here, in the entanglement case, for instance, we know that this state here is maximally entangled when they have the same population on both levels. And on the side, I have a state with a less sort of a weaker correlation by just the fact that this state is unbalanced in relation to this one. In the case of steering, you can also consider this. So we have here an assemblage. I have this component here as an example. Here I show you one type of one of the subnormalized states that that doesn't have the maximal correlation. Here the maximal correlation. So how can I modify my state so that I within that framework of free operations to come to this site here. Sorry. This was done in this case using a local filtering type of measurement, where here we have this operation that the quantum side can perform, so that if we obtain this outcome 0 here, this Q, which is less than 1 and fits so that we can, excuse me, and fit so that we can, with this, recover the amplitude, so equalize the amplitude on both states. And but on the counterpart, since this is a free operation, I cannot create steering out of nowhere. This other outcome here completely destroys the correlation between the states. So with this operation, we can either obtain a state that is maximally correlated within its class, or I destroy the state here with this other outcome. But here with one copy, I have this probabilistically with the probability given by these 2 times the smaller the population, the smallest population of both levels on the assemblage. And here to show how this result scales, so we have, if consider this graph in function of the population difference, and here one of type of quantifier for steering, I show that we have the for an increasing population difference, the initial assemblage loses its amount of correlation, but after the sealing, we have this successful maximally steerable assemblage in a sense. Using more copies, we can make use of the one-way quantum communication, of the one-way classical communication, sorry, to inform the device-independent side on which box it should use, so that in the end we can implement the map on as many copies as we have, except one, and inform the other side, so that if we fail in every copy we perform, we leave one at the end and use that copy instead, so that we can never lose correlation in the process. So this is a protocol which distills, in a certain sense, deterministically, because we can say that we can always, we can never decrease the steering with this method here, using more than one copy. And then the probability scales with the number of copies in this way. So this is an experimental realization. So it was using spontaneously down-converted photons, and which is, here we use 2 degrees of freedom polarization and the momentum that the photon has at the exit of this nonlinear crystal. And in these 2 degrees of freedom, we implement the 2 copies of the original assemblage. In this setup here, we make the measurements on. We consider the side as the side where we don't trust the measurements, and implement the 2 boxes here, the 2 black boxes here. And the other side, we implement the measurements and also that map of the local filtering. So the local filtering is actually implemented here in this mirror, which is semi-transparent, and which is, depending on the position, we can make the amplitudes balanced when it is transmitted, and we obviously lose any type of correlation between this side and the other side if it's reflected. So any type of correlations in the momentum part of the degree of freedom. in the polarization we keep it, and then we make these coincidence measurements to both inform the other part, which type of measurement is being done here in the black box side, and which result was attained here in the quantum side. So the experimental results show that we can obtain this distillation, and here is very clear that we have this big gap here showing that quantum distillation is possible in practice. So I'll be very brief in this, try to be very brief in this second part. So there's another work, so relating to regarding that part of the multiple copies scenario. So here we have this problem. If I have more than two parties, how can I define what is an steerable or unsteerable assembly? So how can I say that in this situation here we have a non-local resource or not? So the first idea that comes to mind is I can say that, well, if these two black boxes here cannot control the state at a distance, cannot they have this classical explanation for the correlations with the quantum state that has in this side, then we have an unsteerable assembly. So we define the assemblage in that in the very same way we did in the two-partite case. But if I consider this assemblage here, for instance, this assemblage is quantum because I can obtain it by implementing POVMs, measurements on a quantum state, and I can also provide a local hidden state model for it. So if I consider 4 different values for the hidden variable, and I consider some quantum states here representing the Bloch sphere and the XZ plane in the Bloch sphere, and I take a certain probability distribution, I can rebuild this assemblage here. But if I allow some cooperation between Alice and Bob, or these two parties here with the black box, if I allow this communication of the result from one to the other and allow the other to use it as an input, what I have in the end is a bipartite assemblage. So I reduce the assemblage with just one black box, which encompasses these two black boxes here after the operation. The resulting assemblage will be steerable. So I can show that this assemblage here, which is the result of this operation, is steerable. So I come from an assemblage which has a correlation explained in a certain way classically, and end up with an assemblage that cannot be explained, whose correlations cannot be explained in that way. So why is that? The thing is, with that composition, the composition for the assemblage, the LHS model, we ended up using some sort of signaling from this party, from the second black box to the first. So here, if I take if I sum out this B variable here, we eliminate this delta, and the remaining probability, which is like the marginal probability seen by this, would still depend on Y. So it would still depend on the choice made by the second party on the black box. So if I do that, if I say that decomposition is possible, and then I allow some communication from the party from this Alice side to Bob, to the choice for Bob, we end up with a causal loop. So this, in a sense, break down this decomposition as a possible decomposition for the system in the first place. So our proposal here in this work was that this shows how we cannot, in a certain way, make this in this definition in a naive way. So we should have a more refined way to characterize the correlations in this multipartite scenario. So here, for instance, I show this time-ordered LGS model where I assume that the probability distribution is signaling from A to B, which is the same way where my the cooperative mod was being performed. And this, so I have to be compatible with the causal. I have to perform my operations compatible with the implicit causal order in my decomposition. This is also being done in an experiment under, so it's being currently being prepared in the Instituto de Física or at the Federal University of Rio de Janeiro. It's being performed by Thais Lima, which is a PhD student there. And so, in conclusion, we can. It is interesting to explore this quantum theory in this scenario because many possible interesting effects are still around, and we may not know. The distillation may have potential for practical applications, and we show also that these naive definitions for quantum steering is not very well. And we have these open problems here. I leave you to the questions, and thank you for the attention.
Thanks.
Yeah.
Any questions indeed?
Yeah. Okay.
Well, not so quick, because I have a question. So I mean, well, once once you have distillation, of course, the question is, do you have some quantity like